So in this lesson I'm going to be talking about one of my favorite units, the Strelley Pool Formation, also back in the Pilbara, and the signs for life and the science that's gone behind really trying to determine if structures preserved in these ancient rocks are made by living communities of microbes or if they might be abiogenetic. The Strelley Pool Formation is about 3.4 billion years old. It's in the same geological area as the Dresser Formation, which is slightly older, but it occurs over a much wider part of the Pilbara. It actually extends for 220 kilometers and is found in all the greenstone belts of the East Pilbara granite greenstone terrain. And that's important because we can do an experiment in one area and then see if that applies in another area where we see similar kinds of structures. And it turns out that many of the structures that we find in the rocks are found in different parts of these dismembered greenstone belts and look very much the same. Importantly, microfossils have also been found from this unit, also from a couple of different localities, and that helps us, be more and more confident that what we're seeing in the rocks are actually an indigenous part of the rock and that it's an important component of the structures that are preserved. So the Strelley Pool is this wonderful succession. It has an unconformable relationship on older rocks, so on the Dresser Formation and on older rocks, and then it has a very well preserved sequence. It's a typical sedimentary transition deposited in an extending or rifting margin. The lowest unit is a boulder conglomerate, and there are boulders up to this big at the base of the conglomerate, and those are typically preserved on a rocky shoreline, a beach deposit. And then you get a unit of clastic sedimentary rocks, sandstones and quartzites, and some beautiful jasperitic pebble conglomerates on top of that. And then you go into a series of very finely laminated dolomites. And it's in the dolomites that we see the first of the signs of life in the form of dominantly coniform stromatolite structures. Anyway, those stromatolites and the dolomites are quite commonly have ripples in them and other evidence of shallow water. And these just look like a typical kind of reef environment. Shallow marine setting, it's continuous over hundreds of kilometers. It's a real widespread unit, very different from the Dresser Formation, which is only found over about 15 kilometers of strike length and has so much variation because of the faulting that's going on during deposition. After you have the dolomitic stromatolites, then there's another succession of clastic rocks, and there are signs of life in those clastic successions. And then you go into a transitional unit where the sediments get finer and finer grain, and then you have pillar basalt. And the pillar basalts extend for about 3 kilometers above, clearly deposited underwater. 3 kilometers, it's a thick section, so the basin must be deepening and deepening and deepening as the volcanics are erupting. So the Strelley Pool Formation really just represents a transition from a subaerial, unconformable sequence through a beach, shallow marine platform, and then into a deep marine basin. And it's in the shallow water deposits that we find signs of life throughout the Strelley Pool Formation. The most common variety, like I mentioned before, are these coniform structures preserved in dolomitic laminates, but also in silicified equivalents. Much of the Strelley Pool Formation is preserved as a chert, but there are rare pockets where the chert is not been completely, pervasively altering, and we have preserved these areas of more primary mineral compositions, and that's dolomite. And that dolomite, we've done rare earth element geochemistry, and it has a typical seawater signature. So we can exclude the fact that it might be a hydrothermal influence or something. It's just normal seawater. And the structures that we find, as I mentioned, are these coniform structures, and Abby Allwood did a beautiful study to show that these coniform structures could not be the product of just mineral crusts. So there had been some suggestion that because of the fine lamination that went around the tops of these stromatolites everywhere, that it was just mineral precipitation that just grew and became amplified structures. But if that's the case, the cone shapes get bigger as they grow out. But in the Strelley Pool Formation, those cones grow vertically with the same width, the same amplitude everywhere. And so these cannot be abiogenic crusts. They're much more consistent with structures formed by microbial communities. Another important observation that was made that these largest coniform structures, they are forming actually on a slope, on a paleoslope, the shallow slope that went into deeper water. And the limbs of these coniform structures are different lengths. On the upslope, they're shallow or they're short, and then on the downslope, they're longer. So they're asymmetrical, and their growth axis is going towards the top. And that strongly suggests that the communities that were making these microbial forms may have been phototropic. The structures are growing vertically towards the light on a paleoslope. But what's even more important in the Strelley Pool formation is that there are structures that are much more irregular. There are large domal structures up to 30 centimeters in height, and they have incipient branches, these wavy kind of structures on the margins. And then right on the edge, there's our most beautiful structure we call the Mickey Mouse ears. It's only a couple of centimeters high and about 3 or 4 centimeters wide, but it's a doubly branching coniform type structure. And it forms just on the edge of a much larger structure, so there's no way that you can argue it's the result of folding or slumping or any other kind of structure. It's just pop, up it goes. And this gets back to the point I made in one of the previous lessons about the interference between sedimentology and biology. So the Mickey Mouse ears, to me, is a very valuable little preserved remnant of a very complex biological structure forming in a sedimentary environment. And we have better evidence for that interplay between sedimentation and biology. You have to get very intimate with the rocks to be able to see these kinds of features. And I've been on that outcrop with many different people from around the world. And I've been there with a couple of geologists who would just stand there and look down from, their standing height, so 1.6, 1.7 meters, and say, oh no, the laminations are all continuous and they just go across the structures. They must be crusts. And I would implore with them, say, come on, you've got to get down and look at them on your hands and knees, get your eyes right up to the outcrop, and you see these actually very important, very delicate features. And on the sides of the cones, if you look very closely, you'll see that individual laminations lap up onto the edge of the cones. There's a discordance between the sediment on the side and the sediment that's in the cones, that's being trapped in the cones by microbial growth. And that shows that these laminae are not just kind of some mineral precipitate, but it actually was migrating carbonate sand that's lapping onto the edge of the structure that's growing above the sediment-water interface. And that, for me, is incredibly powerful. That's that evidence of that interference between physical geology and biology. So if we look again in some more detail at other outcrops, we can see very unusual kind of ripples. They're not normal kind of sedimentary ripples, but they're quite wide and flangy. And if you talk to experts who work on modern microbial mats, they say, yeah, this is just microbially bound sediment, that the biology and the sediment are being interfered with. They're mutually interacting. And then there are other places where you can see very large amplitude sedimentary structures on the scale of sort of 30 centimeters, these big high energy swales. And there's a stromatolite that's growing right beneath it and then cut off by that. You see ripples growing up against the coniform stromatolite. So they're two very clearly different processes, and I think this is very powerful evidence that one of them is a biological contribution. As we continue up through the stratigraphy of the Strelley Pool formation through the laminated carbonates, you get back into a siliciclastic sequence with some boulder conglomerates of black chert and a variety of other materials. And then there are some very thin horizons that are iron-rich. And when you trace those along, many of them are just millimeter laminated, but then they go into these beautiful wobbly kind of shapes. Again, looking somewhat like the Mickey Mouse ears in some places. But those horizons in a different setting don't have the coniform shapes, only these low amplitude, small domical shapes. And when you look in thin section, the tops of those structures are cut off by a little sandy unit. So it's again an interference between a kind of structure made by something that's consistent with biology and then the physical process that planes those off. So this is another type of stromatolites at the Strelley Pool formation. And there's a third type up in sandstones, which just consists of centimeter-thick black horizons that contain suspended sand grains. And when you look at those black horizons, they're made entirely of clasts of fluffy, corrogenous material. And those clasts are made of carbonaceous material. They have a characteristic Raman spectra of slightly degraded kerogen at about green schist facies, and they're clasts within the sandstone. There's no way that they could have been introduced by later contamination or been the product of migration of material because they form rounded grains. And when we look at their organic geochemistry, they have an N-alkane distribution that's very similar to what you find in younger carbonaceous material in other sandstones. And so with these various different lines of evidence, from microbial mats in sandstones, then finely laminated wrinkly stromatolites in very fine-grained chert, and then the variety of structures that we see in the bedded dolomites, this is what we're talking about, convergent lines of evidence pointing to a really abundant and diverse microbial assemblage at about 3.4 billion years ago. Now, the nail in the coffin for many people is that in addition to all of those features, Ken Sugatani has gone through some of those finely laminated cherts, looked at incredible detail, and found abundant carbonaceous structures at a microscopic scale that look all the world like microfossils. He's now published a number of papers from two main localities of the Strelley Pool formation, and they are very similar morphologically to what had been described from rocks only slightly younger from South Africa. Odd, almost spaceship kind of microfossils, quite large, and they have a central hollow core, and then these flanges, or that makes a spindle shape out of the margins. And you find some in irregular lumped groups, but then also as trains of microfossils. They're very unusual structures. And again, their carbon-13 ratio, their carbonaceous nature, all of those features are consistent with biology and very hard to explain by any other mechanism. So although there may not be a single smoking gun at the Strelley Pool formation, the diversity of lines of evidence all pointing towards the same thing, to me, make a very powerful narrative about early life on Earth.